I think we also start streaming to YouTube again. And yeah, so this morning we have topics on medical related topics, and then in the afternoon we go to nuclear energy related topics. Let's start, jump right in, so we don't already start with a delay. So I welcome, well, I say first, hello and good morning to everybody. And I say good morning to João Seco, our first speaker. João, I'll let you present yourself and just already jump into your presentation.
Okay, thank you very much, Kirsten. I work in Heidelberg. I head up the division of biomedical physics and oncology. And I'm a physicist by training, so you can ask me really the funny, hard questions in physics if you want to. I've also spent many years in the US doing medical physics in the clinic and translational research. So the talk I will be talking about today, the topic will be proton therapy. If there are any questions, I kindly ask that you keep them to the end, or you can write them in the chat. It will be easier. All right. So if I can get my computer to work. All right, so this is a rough overview. I'm sorry for the Coimbra over virtual, but this is just a, oops, sorry, my mistake here. Okay, so overview of the class. I will give an introduction to proton therapy and a historical overview. Then I'll give an idea of how it works in the clinic from research facilities to hospital facilities. And I'll progressively move from basic introduction to proton therapy to the application for imaging and motion and even for oncology. So the person that had the breakthrough idea was Robert Wilson. He published a famous paper in 1946.
Excuse me, João, we can't see your presentation anymore.
Oh, I'm
Something
sorry.
happened there.
So can you see it now?
Now you started screen sharing again. Yes, exactly.
Okay, my apologies. So the person that had the breakthrough idea was Robert Wilson in 1946. He published this famous paper. And this was kind of the first person to say that we could use protons for therapy. And in this famous paper, there was a few things. Protons can be used clinically, accelerators are available, maximum radiation dose can be placed within the tumor. Proton therapy provides a way of sparing normal tissue, which was really a breakthrough idea that radiation can spare tissue in addition to treating the cancer. Modulator wheels can be used to spread out the Bragg peak or to create multiple Bragg peaks. I will explain this further down. And here is more or less the person itself. He lived from 1914 to close to 2000. And he basically was the first person to drive the idea. And then it took about 8 years until the first application at Lawrence Berkeley Laboratories in the US of proton therapy. And then in Europe, the first center was Uppsala to treat. And then it took another 20 years for the use of carbon ions. So from 54 to 75, it's over 20 years, where they started using carbon ions, again at Berkeley Laboratory. So these were the first 20 years of fundamental research into particle therapy. So it was very different the way they did that to what we do today. And then the first hospital facility happened to be in Loma Linda in California, if you know where it is. It's 2 hours east of LA. And a small town called Bernardino, and very close to Bernardino, in fact. And this is the first hospital facility to treat with protons. In Japan, the first carbon ion therapy facility was Chiba. And in Europe, the first one was at BSI in 96. Okay. So these are 3 steps: research, clinical research, and finally clinical application. So the first real hospital systems, for example, for carbon was in 2009. But before that, Heidelberg had acquired a lot of experience by working in Darmstadt with GSI. So the first 12 years of treatments in carbon ions in Europe were done in GSI Darmstadt. So the patients in Heidelberg were driven to Darmstadt, which is about 60 kilometers north. And then the patients would be driven back to the hospital. And then in 2009, the first ion therapy facility opened in Heidelberg that now treats everything directly here in Heidelberg. Then there has been a variety of other centers that have opened: Knau, Hyogo, Gunma in Japan, these two in Japan, Med Austria in Vienna. So there is a variety of centers that open. So just to give you an idea of the difference of how it looked many years ago. So this is how you would treat patients. It looked like a lab. So you see this whole lab construct with all these little pieces all over the place, boards, patient treatment, a mask. So this is a flexi mask on the patient for positioning, and the beam would come in from the right. So this is how we would treat up until really roughly 1990 with the first hospital facility. Now, if you look at the modern day treatment facility, it's something like that. So it's completely different style. So the patient basically doesn't get to see what's under the box, right, or inside the box. So you have a robotic arm here for positioning. You have a gantry rotating for multiple angles. You have a patient sitting on a blue bag, which allows you for positioning, and everything is computer controlled. And you see the control room computers here on the left and the right, which are connected to the outside room where you have the room. You also have these laser positioning systems up here, and you have a little camera system to check on the patient. So this is modern hospital facilities. I'm sorry I present accidentally the name of a company. I'm not advertising any company. All right. So the operation of centers has increased exponentially over the last years, but it took many years until they started to grow. Right? So from the 1960s, you see a very slow growth. Most of the centers were national laboratories. Then you start to appear the hospital-based systems, which had so-called scattered beam. So a scattered beam is something that allows you to deliver a broad beam, very much like in photon therapy. And then with increase in the quality and engineering, they slowly progressed into a third generation proton facilities, where now all the treatments are done with scanning beams. So the scanning beams are more or less, it's yellow. And now all the new therapy facilities in protons are scanning beam based. So all the blue ones are scattered beams, and all the yellow ones, which are the new facilities, are scanning beams. I'll explain the difference in a minute. This is more or less the centers spread all over Europe. I'm not sure if this is completely updated. There's maybe 2 or 3 dots missing. All the orange dots are proton facilities, and all the purple dots are carbon ion facilities. Right? There is one other carbon ion facility that's here close to Cannes, which is yet to become operational. So where there's proton center, there will also be a carbon center here. And then there is a variety of other places. And there is also one estimated in Oslo here, in Norway, and there's a variety of other centers estimated. So you see there's an increase, and there's some also in Eastern Europe, in Moscow and St. Petersburg. And in Spain, now there's 2 new ones that just opened a year and a half ago in Madrid. Okay, and then there are a few other centers planned. In London, there are now 2 possible centers opening, and 1 in Newport here in the bottom next to Bristol. There will be other centers here also opening soon. Okay, so this is how it looks, the Loma Linda proton facility. You have the accelerator section here, where you accelerate your ions or your protons in this case. It's a synchrotron accelerator. You have your beamline structure, which transports the beam into the treatment rooms, and these treatment rooms are 3. You have 3 gantry rotating rooms, and so the beamline transports them into the gantry to treat the patients. And then you have an additional stationary beam section here, which is primarily used for research, but you can also treat. And then you have another one here. You have a second 2 stationary lines. You have one potentially for research, and other one for clinical research for patients, stuff like that. And these were all passive scattering. I will explain that in a second. Okay. Here's the one that exists at MGH in Boston, where I was for 12 years. We had in Boston a cyclotron, not a synchrotron system. We had the beamline transport into 2 gantry rooms. And then we had a 3rd room, which was dedicated to radiosurgery, to eye. And then we had a special research corner here where we used to develop things, right? So there was basically ultimately 5 positions where the beam would come out, and they were specifically for different designs. The treatment room 1 and 2 were primarily passive scattering beams. And then in early 2008, 2009, we commissioned the pencil beam scanning system. So they now allow both systems. In the case of the radiosurgery, the beamline is a fixed beamline, and what rotates is the patient. So the patient is on a robotic system that rotates the patient to allow any position of angle. And here in the ocular system, you have basically a chair, the person sitting in a chair, which keeps the head in the right position for treatment. And just an idea, the cyclotron system that is used for accelerating the protons is roughly diameter of 4 meters. This is similar to a PET cyclotron, just about 10 times larger, right? So PET cyclotron that you use for accelerating to produce PET is usually half a meter to a meter. An IBA proton system for proton therapy is usually 4 to 5 meters now. And this is the HIT facility in Heidelberg. We have here a synchrotron, which accelerates the beam. You have 2 injectors for different ions. One of them would be protons and helium on one side, and the other would be oxygen and carbon. And these injectors accelerate them through a linear accelerator. So there's a small section here that accelerates the ions to enter the synchrotron, and then they get accelerated in this racetrack approach. And then you have the delivery to fixed beam lines. So you have a fixed beam line here for 1 or 2, and you have a very big gantry room to allow any type of position. And then there is a 4th line here for research, where most of my PhD students and postdocs spend most of the nights working here in this experimental line. So the gantry here is humongous. So it's really huge. It's a 600-ton gantry. It's probably the biggest worldwide. And I don't think there'll be anything at that level. Most of the gantries now are extremely small. So the next generation of facilities, well, so the key is now to make things smaller so that you can reduce the cost of building these things. So definitely compactness is a major important thing in the next generation facilities. Then you have in-room imaging is really important for ions, and there are 2 major problems. One of them is anatomy tracking. So if you've read a lot about MRI LINAC, anatomy tracking is related to MR or X-ray imaging tracking of anatomy. But in ions, we have an additional problem, which is beam tracking. You have to know where the beam stops, and you need to do some form of beam tracking. So these 2 problems are really important, and you need in-room imaging for that. And then there's the new protocols related to flash and other things. Okay, so the HIMAC facility in Japan, they have now developed a mini version of these gantries. They are now much, much smaller with the use of superconductors. So in this case, you can use the superconductors, which are much smaller, and you can have a size of around 8 to 10 meters, and the reduction in weight is significant. So you can have probably 100 tons or less now. Some of the carbon ion gantries can even be in the orders of 60, 70 tons. So it's really important that by reducing the gantry transport of the beam, you reduce the footprint of each room. And this is ultimately really what you want. So minimization is really a key, both to the cyclotron or synchrotron and to the gantry. So in-room imaging is really important for particles. And I put this really famous picture from one of the review papers published a few years ago, that if you look at an orange and you consider that the cancer you want to treat is this orange part on the right, and then you add a margin to generate your PTV, the margin is very thin. It can be only a few millimeters, 4 or 5 millimeters, but the total volume of this margin is very big. So although you have a very thin margin, the total volume is almost comparable to the tumor. And so you have to keep in mind in radiotherapy, the side effects are proportional to the volume that's irradiated. So yeah, I've doubled the volume just with the margin. So I increased side effects because of that. So it becomes really important to reduce this margin as much as possible, right? If I reduce the margin, I reduce the volume that I radiate. That's usually healthy tissue. And this reduces, of course, the potential side effects. And so there are different types of in-room imaging. Here is a gantry mounted cone beam system from Mobius. And you see here's the HIT facility with the fixed beam line. And you have a gantry mounted system that's going to move up and down to allow positioning, daily positioning of the patient. That's one approach to it. Another approach, so this is a positioning system that allows it to track the anatomy. So cone beam is an imaging that allows it to track anatomy. So you can either do bone imaging, or you can even potentially have anatomy tracking. Another problem is the so-called the range problem, right? So you need to do the beam tracking. And there are different ways of doing this. One way is to track directly the beam via the emission of secondary particles. One of the most important secondary particles that come out is the gamma. So you irradiate with a proton beam. It hits the nuclei of different atoms like carbon or oxygen. These nuclei de-excite with the emission of prompt gammas, and you use these prompt gammas to localize where the beam is. Right? So this is a beam tracking system. You don't really see the anatomy, you see the beam. And with the beam tracking system, you can see the Bragg peak. Right? You have two images, yeah, which is the two yellows, which see the prompt gammas, and you see the Bragg peak. You basically localize it. And so the trick is to have a red beam line, a beam coming in that produces a Bragg peak. You take an image of all the prompt gammas before and after the Bragg peak, and you localize where the Bragg peak is. And this can be done real time, more or less at the millisecond level. So you have real time imaging of the beam. And ultimately, you always want to put the two of them together so that you know where the anatomy and the beam is, so that you have maximum control of the treatment. So I have a small slide to kind of describe, 2 or 3 slides to describe the importance of protons. And I think these would be the important slides that you should follow if you don't understand clearly the difference. Just a quick overview of the interactions. So the main interactions of protons as they go through matter are electronic interactions. So they interact with the electrons of the atoms. They either ionize or excite electrons. So this is an ionized electron, for example, and you can have an excitation. You can also have nuclear interactions. So in this case, you will have elastic scattering of the nuclei, and you have so-called Coulomb scatterings. And if you put many of these Coulomb scattering together, you produce something called as multiple Coulomb scattering. So multiple Coulomb scattering is not a physical interaction. We just use it to define multiple Coulomb scattering happening in a row. Right? So this is an elastic scattering of the nuclei. You can also have a large, where you have a recoil nucleus scattering. And then you have the non-elastic nuclear interactions where you can have the breakup of the nuclei. So you produce a radioactive element at the end. In this case, you have the breakup and you produce either gammas or neutrons or other secondary protons, and you have a recoil nucleus which is broken up. Right? These are the main interactions. Okay, so the depth dose properties here are represented in orange, in yellow is the photon beam that is usually compared to protons. You see a maximum depth dose for the photon beam, so say 15 MeV beam. Then you have your Bragg peak in blue dotted line. In blue dotted line, and then you have what is called the SOBP, where you make a spread out Bragg peak with multiple Bragg peaks. Usually you need to create a region of irradiation which covers the tumor, so you need multiple of these Bragg peaks put together to create the so-called tumor region of treatment. And the first thing that you notice is that the X-rays deliver more dose both at the entrance and at the exit, while the protons don't have any exit dose. It's literally 0 dose here. And that means that I can spare all organs on the outer side, on the distal side of the proton Bragg peak. So also important thing to notice, there is a maximum, and so you control this Bragg peak. The rapid distal fall off is very important. This distal fall off is very fast compared to other beams. You can modulate the energy of the beam and so that allows you to shift this Bragg peak in depth closer to the surface. So this modulation is the so-called done with you can do it with range modulators, or you can do it with other forms. And the good thing about protons is they also have a RB very close to that of photons, roughly 1.1, which means that there isn't a big transition from photons to protons if you're a clinician. So here's the curve that is most important to really understand proton therapy. Here on this side, I have on the red, I have tumor control probability on the y-axis, which goes from 0 to 100%. And on the x-axis, I have dose, radiation dose. If I increase the radiation dose to my tumor, eventually I will achieve 100% control of the tumor, right? I can give 100 gray, 1000 gray, eventually radiation will kill all the cells present. The only problem in patients is, as I increase the dose to my tumor, I also increase my dose to the healthy organs. So I get what is a side effect, which is called toxicity. So when we do radiation, we always have these two curves, the red curve for the tumor, the white curve for the organs at risk. And in photons, the distance between these curves is usually small, and the white curve is offset to the right because it usually represents better DNA repair. So healthy organs have a better repair mechanism, and they can survive. They can sustain higher doses of radiation. That's why they're offset to the right. In the case of treatments, you would like to be always in this midpoint here. This is your so-called benefit point for treatment if you treat photons and if you use photons to treat the cancer. And so For a certain level of toxicity, I've put 20% toxicity, I get a tumor control, in this case, around 30 to 40%. So you see, it's not optimal. In fact, I have a very poor tumor control with this level of treatment. So what's the advantage of using protons? Well, the protons, because I reduce the dose to healthy organs, I shift literally the white curve to the right, and I have a new toxicity curve. And ultimately, that means that at the same level of toxicity, I have much higher tumor control. So you see here that the tumor control with protons has gone up to around 80 to 90%. So for the same level of toxicity, I can achieve a much higher tumor control, and I provide the patient a better probability of surviving cancer. And this is the most important slide. To understand this, then you understand how protons work. We reduce the dose to organs at risk, and therefore it allows us to increase the dose to the tumor. So at the same level of toxicity, I achieve much higher tumor control. So this is a famous quote from the clinical director for MGH for many years, Herman Soot. He used to say, there is no advantage in irradiating uninvolved tissues. And this is really the maximum of proton therapy. We don't really want to irradiate healthy tissue. We want to just focus on the cancer. So now I come to the delivery methods. There are two main methods, the passive scattering systems and the pencil beam scanning. They're more or less a historical progression from passive to pencil. And more or less what I want to do is to deliver a radiation dose to the tumor. So here's my tumor in orange, in dark brown, sorry. And I have 3 beams coming in. And all these 3 beams, they are uniform, right? So you see a uniform dose, and I produce a uniform overlap, right? So I see an SOBP here, spread out Bragg peak, and it's usually called single field uniform dose. So one field is uniform. And if I put 3 single field uniform doses together, I get a uniform dose distribution. And this allows me to treat the tumor with 2, 3, or 4 beams. Another way to treat is to use IMPT, which is intensely modulated proton therapy. And now I don't have a uniform dose per beam. I have a modulated fluence. And with this modulated fluence, I can generate any shape that I want to treat. So here I have a diamond just to make it different. But the modulation allows me to generate any type of shape that I want ultimately. So here's an example of a passive scattering system, the one that existed in MGH. And it is a pretty complex system. It ultimately starts with a very narrow beam of protons coming in. Then you have what is called a range modulator. And each range modulator is just tiny steps of 3 millimeters of absorbing. And with the range modulator, you change the energy of the beam. So you can basically do a pullback of 3 or 4 or 6 or 9 or 12 millimeters, depending on the depth of plastic that the narrow beam is going through. Then you have what is called a double scattering system. Here, first and second scatter to broaden the beam. So you have a narrow beam, which is then broadened to achieve a broad beam. And then with this broad beam, then you shape the beam with a compensator. So this range compensator modulates the distance of the Bragg peak to the distal part of your tumor. Right? So here's my tumor part that is shaped with a compensator. I produce more or less a U shape here. And this U shape propagates in depth. So I lose control at the entrance part, but I have excellent control at the distal part of the tumor. And then this aperture is just the shaping device, the open area. So the compensator is this one that is used to modulate to the distance, and the aperture is this one here. So effectively, it looks something like this. You use a compensator to shape the distal part of the tumor, but you lose control at the entrance. So you give an extra dose here, and it's usually very high doses in these 2 entrances. But you're already sparing organs like this orange one here, this yellow one. You do lose some control on this one, so here you would need IMPT for this. So here's the same system that, for example, is available at the HIT. You can have a scanning, this is a scanning system. And in the scanning system, you can have energy modulation upstream, and you need magnets to scan up and down. This is like a television system where you scan X and Y, and so X and this one and Y, and you use these wire chambers to tell you how much fluence is going through, and you can scan line by line. So you see these lines of planes where you're scanning, and you can scan any depth, any position. So that's why it's called pencil beam scanning. You're scanning like a television, and you scan through through each plane, yeah, and you do energy modulation upstream here. and you produce any Bragg peak with the energy modulation. So here is SOBP that is produced, for example, with a passive scattering system. I have multiple Bragg peaks put together, different levels, and they produce a flat beam, a flat region here, which is used for treatment. And in that case, the SOBP can be produced with the ridge filter, which is what we have here in Heidelberg, or range modulator system that is at MGH. And you see the steps of these plastic. And each step is approximately 3 millimeters of absorption. So 3, 6, 9, 12, and so on. So you can absorb up to as much as, 100 centimeters, not 100, 100 centimeters in depth, yes. Sorry, not 100 centimeters, 20 centimeters in depth. So the range modulator is this part. Pay attention that that is usually done with a narrow beam. You have your double scattering systems that broaden the beam, and then you have your compensator. So here is the passive scattering system that I would deliver. You see the horns of the problem. So you have horns here in high dose. You have good shaping in the distal area. But if I use the pencil beam scanning, just overlapping now, I lose these horns, and I have a shaping line by line. So now I have a beam that's scanning layer by layer and delivering to all these points. And I don't have any more of these hotspots that I would see here with the range compensator. So the passive scattering system is good for shaping distal part, but it's poor for shaping at the entrance. While the pencil beam scanning allows you to shape both distal and proximal side. And that's the advantage. That's why people have commissioned all the new beams to be pencil beam scattering, pencil beam scanning. So I did some commissioning of our first system in Boston with Ben and all the rest of us. Jay Flans and Hanukui were the head of the research at the time. And so Ben and myself, Nick and Carlos, we did a lot of the work for the commissioning of the first pencil beam scanning at MGH, and the second one in the US, in fact. And here is the commissioning data. We needed to calibrate the system here on the left. We produced a lot of Bragg peaks for different depths. So all these Bragg peaks have for different depths in water, up to 34 centimeters, I think it was. And we use this information to commission a system and to also build a treatment planning system. At the end, the model was extremely good. So the experimental data with the fit and the model that we developed, so-called golden beam data, then fitted the system, and it was a pretty good estimate. And then when we produce SOBPs, you see the experimental data is usually the dots, and you see the lines of the model. So it took a long time, almost a year and a half to do, but eventually it worked out really well. All right, another thing that is extremely important is imaging, pre-treatment imaging, and for moving targets. I will just point out that a lot of the pre-treatment imaging is the clinician's responsibility. They are responsible for pre-treatment staging. But another part that is important to the physicist is the pre-treatment imaging for stopping power estimations. And so you have dual energy estimates. You have Siemens, GE, Healthcare, and so on. And these produce two spectrums, low energy spectrum and a high energy spectrum mostly. And you need these two spectrums to be separate. So that the key problem is to identify the two things, which is the electron density and the Z effective. And there are two ways to do it. Either you break it up into two cross sections. Here is a photoelectric cross section, the Compton, and you have a parameterization alpha beta that you have to identify with your dual energy. And you can do it like this. This is what they do in radiology department. In the radiology department, they develop two scans, a water scan and an iodine scan. And the iodine scan is the one that's representative of your photoelectric effect. In a normal radiotherapy department, we don't do it like that. What we do is we fit experimental data. Hello? I think my computer is just frozen.
Okay, we can.
Okay, let me see. Yeah, I think my computer just froze. I'm sorry. So I think I will have to stop here. I cannot access the computer anymore.
Okay, can you, well.
Okay, hold on.
Zhao, we're coming to the end anyway. I mean, if you, I mean, can you maybe summarize the
I wanted to do that. So let me just do that. So I apologize for that. My computer just froze at the end for the first time that's happened in a presentation. So in proton therapy, it's really important now to do estimates of pre-treatment stopping power. And this is the main focus is now dual energy. And a lot of systems out there also developing beam tracking systems like the prompt gamma system I showed. And ultimately, we want to try to provide the clinicians with the best estimate of dose as we go in. Proton therapy has a big advantage over photons from a organ tissue sparing perspective, and I think this is the main drive for people to use proton therapy. And I'll finish with that.
Okay, thank you very much. It's more amazing, lots of information. May I ask, are there questions? I don't see any questions in the chat, but maybe somebody would like to speak out and ask a question. I don't see anything. But I guess, Zhao, you showed your email address. Maybe you can put it into the chat as well, so people can address you directly with questions by mail. Then.
Absolutely. Please do contact me with questions if you have any questions. I apologize, my PowerPoint froze for the first time, and so I got stuck on the stopping power.
That's the pleasure of life, being live.
I would have some questions.
Okay,
Tobias, yes, please.
Yes, regarding the safety installations for patients and staff, I wanted to know what kind of detectors are employed. I expect some sort of detectors to be employed to measure the radiation in these treatment rooms and around them.
So for radiation protection or from a dosimetry?
Dosimetry.
So most of the ion beams have ion chambers at the top, which are used to measure the dosage coming into the patient. And if we use in vivo measurements, we tend to also use ion chambers, unless you're doing skin doses. Of course, that's a bit more tricky, and then you might use PLDs or rectals.
I have difficulty hearing you.
Can you hear me now?
Yes, it's better. Yes.
Okay, so ion chambers is the standard for ion therapy, very much like photon therapy. There's no big difference there.
Yes.
So all the dosimetry is based on ion chambers.
Okay.
That's for dosimetry perspective. It doesn't work for flash, although I don't know. I didn't get into the flash part, but ion chambers are not so good for flash. That's the only issue that I usually say.
Okay, thank you.
Okay. So thank you very much. So again, yeah. So let's jump then directly into the next presentation. It's from David Legrady. Unfortunately, David cannot be with us this morning. So I'm asking Mattia, our hero in the background, to launch the video. Mattia?
Yes, here we are.
Just for 2 words, David Legrady tomorrow will be with us whole days, and you can ask in live also. And keep in mind your questions, and you can ask from him. Thanks.
Okay, Sila, maybe you can also put the email address of David into the chat so people can ask questions. I think sometimes if it's fresh, they just put questions into the
Okay.
by email. Okay.
And the introduction of David you can find on the web page. He is associate professor in Budapest University of Technology and Economics. He works in a medical imaging field and Monte Carlo simulation also. Thank you.
Okay, thank you. Okay, Mattia, I see that the picture here is a bit blurred. We always have this problem every now and then.
I suggest to follow the link to YouTube. Maybe the quality sometimes is better there.
Yeah, we had this yesterday, so that the link on the image on YouTube is better than here, unfortunately. But let's see. Sometimes it's getting also better. So, are you ready to start, Mattia? Let's go ahead.
Hi there. That is David Legrady speaking.
Thanks.
I'm teaching medical physics at the Technical University of Budapest. I'm really sorry I can't be here with you in person. I mean, I'm not giving this lecture live, but due to some family obligations, I could not. I'm going to join you tomorrow with live presentations, but today it is now offline. What I'm going to talk about is how to create a medical image, but for that first I'm about to talk about how to create an image at all. Now we are not in the same lecture room, you can't see me. I could install a webcam, actually I did, but maybe first I will show an image of myself, so you will see who is talking to you. What I'm going to talk about today is how an image is born, any image. And how would you translate that imaging process, this image creation process, to medical imaging? And what I'm migrating towards is how to create from loads of images a so-called tomography. Maybe some of you do not know what tomography is. If that is the case, I hope in one day you will know. In case you do know, I definitely hope that you will understand it more than before. I'm also going to talk about the machine, the medical equipment that provide the data that we can use for tomography. So now about the image of myself. This is the image of myself, and I definitely hope you can see me very well, recognize me, all my features. I leave this image for a while because you may need some time to see me in it. What I have done, I took a portrait image of myself, and for every pixel I recorded the intensity of that pixel, and I've put it down for you. Every line, every pixel. Okay, it is a smaller version because otherwise it would not fit the screen with all the numbers. I definitely hope you can see every single number in it. So now you can imagine how I look like.
Hello, everybody. I think the image quality is very bad. Well, here on Zoom, but on YouTube as well.
Yeah. I think that I'm going to give the direct link to the video because the video is better. And in this case, they can look at.
Okay, but I saw that our next speaker is already with us, Tibor. I suggest maybe that we
Yes, and in this way everybody can see this video alone because this quality is very low.
Yeah, exactly. Okay, so let's do it that way. Let's Tibor, can you hear us? Are you with us? I don't know whether he's already ready. So we will.
Yes, I'm here.
Yeah.
Okay,
Sorry
can you hear me? Okay, I just need maybe 1 minute to prepare my presentation, okay?
Okay, so and in the meantime, we are going to repeat to everybody. So what Sila is going to do, Sila is going to send us a link to the video. I guess it's the Google link that we have, and then everybody can can watch the video on his or her own. Again, apologize for this. I mean, that's what happens if you're live. But I think it's really better to do it that way than rather than going through trying to follow something with very bad quality. Okay, Tibor is getting ready.
Okay, I'm trying to share my screen.
Perfect, it's coming. Okay. You're not yet on presenter mode.
Just a minute.
Yeah. No, this is this is your presenter mode, so we can still see the next slide. Are you working with two screens, maybe?
Yes, but can you see the?
Now it's perfect. Now it's the right screen. Now you're showing the right screen.
Okay.
Okay.
Thank you.
Thank you, Tibor, for being so flexible. So, okay, so now we're talking about brachytherapy. Tibor, maybe you can present briefly yourself, and then we jump right into your presentation.
Okay,
thanks.
I welcome to everyone. My name is Tibor Major. I'm a medical physician working here at the National Institute of Oncology, Budapest, and I also working at the Semmelweis University, Budapest. So in this presentation, I will speak about brachytherapy. You maybe not know what brachytherapy means, but I will explain you shortly. So probably you know that radiotherapy is a type of treatment, and in radiotherapy, ionizing radiation is used for killing cancer cells. And brachytherapy, which is called also internal radiotherapy, is one of the forms of radiotherapy. So during brachytherapy, we use sealed radioactive sources, and these sources are placed in or close to the tumor. And because of this, very high doses develop near the sources, but due to the steep dose gradient, the dose decreases with the distance rapidly. And this is the main factor in brachytherapy, this high dose gradient near the sources. Anyway, the brachy word this is a Greek word and means short distance. So this refers to the meaning of the brachytherapy, because with brachytherapy, we irradiate at short distance and we can deliver locally high dose, and the same dose, the surrounding normal tissues receive relatively low doses. Okay, on this slide, you can see the events at the birth of the brachytherapy. At the end of the 19th century, Becquerel discovered the natural radioactivity, and a few years later, Pierre and Marie Curie discovered the radium. A little bit later on, artificial radioactivity was discovered by Irene Curie and Frédéric Joliot-Curie. And these discoveries were so important that in a few years later, Nobel Prizes were given to Becquerel, Pierre Curie, and Marie Curie for the discovery of spontaneous radioactivity and their joint researches on the radiation phenomena. And a few years later, Marie Curie received another Nobel Prize in chemistry for the discovery of the elements radium and polonium and isolation of the radium. So a few words about the sources and equipment used in brachytherapy. In classical brachytherapy, the radium was the radioactive isotope, which was used mainly as needles or tubes. Later on, iridium-192 and iodine-125 became available. The iodine-125 in form of seeds, either fixed in a ribbon at 1 centimeter separation from each other, or in the so-called loose seeds form. The iridium was used in wires, mainly in France, but the most common type of the source is the stepping source. Here you can see the main physical characteristics of the isotopes used in brachytherapy. These are gamma radiation sources. As I mentioned before, the first isotope was the radium, but nowadays it's not used anymore due to the radiation protection issues. The most common radioactive source is the iridium, iridium-192. The half-life time is 74 days. The mean energy is 0.38 mega-electron volt. Iodine-125 is also used. It has less half-life time, and its energy is much less, only 28 kilo-electron volt. You can see the decay of the iridium-192. It decays in two forms, electron capture and beta decay. But after these two processes, the gamma irradiation is originating, and only the gamma irradiation is used for the treatment. You can see the energy spectrum of the iridium. You can see there are many energies, even more than 1 mega electron volt with less intensity. But as I mentioned before, the mean energy is around 380 kilo electron volt. A few words about the dose rate definitions. In brachytherapy, we use these terminology: low dose rate, medium dose rate, and high dose rate. We speak about low dose rate when the dose rate is less than 2 gray per hour, and we use the high dose rate when the dose rate is higher than 12 gray per hour. In classical brachytherapy, only low dose rate sources were used with manual technique, but later they were replaced with the HDR, high dose rate source, using the afterloading technique. And currently, high dose rate is the most commonly used dose rate. What does this afterloading technique mean? It means that the catheters or applicators are placed in the patient in a non-radioactive environment, and the radioactive source is loaded into the patient at a later time for the treatment. This is a very safe regarding radiation protection of the staff, because during the application there is no any radiation, and when the radioactive source in the patient, the staff is outside of the treatment room. That's why this is the most common brachytherapy technique worldwide. Here you can see some afterloading equipments. They look very similar. They are mobile units, and practically they are working with the same technology. Here you can see the afterloading equipments used at our institute. On the left side, this is our former unit. And here in the middle and the right, you can see the current equipment, which was installed just a half years ago. This slide shows the main parts of an HDR afterloading equipment. This is the head of the equipment. And there is a source container in the middle, and the radioactive source is positioned in its center. It is important that only one source is in the equipment. And there is a stepping motor here, and this motor can drive out the source through this transfer tube to the applicator, which is inside the patient. And after that, it pulls back to the container. So this is how an afterloading equipment works. This slide shows some physical properties of a high dose rate source. Here you can see the physical dimensions of the source. The length of the capsule is around 4.5 millimeter, and the diameter is less than 1 millimeter, very, very small, 0.9 millimeter. And as you can see here, this capsule is fixed to the wire. Here you can see this wire, and the source is moved with this wire using this stepping source. This image demonstrates how we can shape the dose distribution using a stepping source. This is an autoradiography, and there is one straight catheter here, here, and here, and here. And the source, the radioactive source, was stopped at different positions for different times. Here, just at both tips of the catheter in the middle. Here, continuously increasing time. Here, larger treatment time, no treatment time, larger treatment time, and so on. You can see that changing the irradiation times, the dose distribution can be very nicely modulated. This is only in two-dimensionally, but you can imagine if we have many catheters or needles arranged in a three-dimensionally, then we can shape the dose distribution very nicely to the shape of the target volume. This is called the so-called conformal radiotherapy. Let's see the dose calculations. If we have a one-point source, the dose is inversely proportional to the square of the distance, resulting in a high dose gradient around the source. But in addition to the inverse square law, the absorption and scattering in the medium has also effect on the dose distribution. Here on this graph, you can see the correction factor for iridium, radium, and iodine isotope. For the iridium, you can see that these two phenomena, the absorption and scattering, cancel each other, and the correction factor is very close to 1 in a few centimeters from the source. What does it mean? It means that the dose distribution in an air will be exactly the same as the dose distribution in the water when the medium is surrounded, when the medium surrounds the radioactive source. But anyway, the dose inhomogeneity is evident in brachytherapy, and its magnitude is an important issue. But in a clinical practice, we don't use point sources, but we use very small line sources. So here you can see the factors contributing to a dose distribution around the line source. Here, this is the radioactive material, and this is encapsulated. This is a small capsule, okay? And this is the point of interest, and these 4 factors which determines the dose at the reference point. The distance, if there is a very small point source inverse square law, the attenuation of the gamma rays by the source and the capsule itself attenuates the source, attenuation of the photons in the medium, and buildup of the scattered photons. So these factors have to be taken into account during the dose calculation. Two-dimensional geometry is used for the calculations. Here you can see a radioactive source again, and this is the coordinate system, and the reference point is at 1 centimeter from the source, perpendicular midline to the source, and everything is related to this reference point. And if we are in a point and we want to calculate the dose rate, how can we do that? For this calculation, the American Association of Physicists in Medicine worked out a formalism. This is the called TG43 dose calculation formalism. And this is the equation which shows how we can calculate the dose rate in a point, characterized by a distance and the theta degree. So there are a few parameters. The first one is the air kernel strength. This is what the users have to determine with source calibration. This is the only one parameter which has to be checked by the users after the source replacements. The next parameter is the dose rate constant. There is a geometrical function which takes into account that we don't have a point source, but a linear source. For the point source, this is the inverse square law. There is a radial dose function which takes into account the dose distribution along the midline of the source, and there is an anisotropy function. Anisotropy function takes into account the source distribution in the line source. And if we use this dose calculation formalism, we can calculate the dose distribution, what we can see here. In the middle, this is the small line source, and this is the relative dose distribution for the iridium-192. You can see the anisotropic dose distribution because of this linearity of the source. And if the relative dose is 100% at 1 centimeter here, and we increase the distance to 2 centimeters, the dose will be only 25%. So this is the consequence of the inverse square law. And this very nicely shows that close to the source, high dose can be delivered. And if we increase the dose, increase the distance from the dose, from the source, the dose decreases very sharply. A few words about quality assurance. Imaging is always used before brachytherapy treatments. With imaging, we can reconstruct the source positions in 3-dimensionally. With this phantom, the accuracy of the imaging and the reconstruction was checked. There are many small metal spheres in this phantom, and their coordinates had to be determined with imaging and reconstruction. And this is the result. Here you can see the mean deviation of the real coordinates, and the calculated coordinates is around 0.1 millimeter, and the maximum deviation was only 0.5 millimeter, less than 1 millimeter. This means with this imaging and with this reconstruction software, the coordinates of the source positions can be determined very accurately. The source has to be calibrated after the replacement, and these are the equipments which can be used for the source calibration. There is an ionization chamber on the left side and the electrometer. In the video, in the practical video, you can see more details about the source calibration. The source positioning accuracy has to be also checked. Here you can see the images using autoradiography. So the film, on the film, straight catheter were placed on the film, and at 1 centimeter separation, the source was stopped here. And on the film, we can see where the source stopped, and we can check the positions. We can measure how accurately the source was moved between the different positions. You can see the movement was 1 centimeter. The step size was 1 centimeter. In the middle, you can see the setup. This is the film and the catheter on the top of the film. And here again, you can see these black holes where the radiation source was stopped for a few seconds. On the right, you can see the so-called ring applicator, which looks like a ring. And this applicator was placed on an autoradiograph film. And here you can see again the positions of the radioactive source. Finally, some clinical application of the high dose rate brachytherapy. Here you can see different catheters, applicators, and needles. Depending on the treatment sites, metal or plastic catheters or applicator used, and depending on the type of the imaging, sometimes MR and CT compatible applicators have to be used. This is an example for the breast cancer brachytherapy. The tumor has been removed, and after the surgery, the tumor bed has to be irradiated to kill the cancer cells in the cavity wall. That's why we insert small catheters into the breast, and after the imaging, after the CT imaging, we delineate the treatment volume, the target volume. This you can see in red, and the other anatomical features, for example, the lung and the breast and the skin and so on. These are the catheters, And after reconstructing the catheters, here you can see in three-dimensional reconstructed catheters and the target volume. With a special software using optimization algorithm, we can calculate the source positions and the source irradiation times. And here you can see the final dose distribution. Here there are two red lines. The thick one is the target volume, which has to be irradiated. And the thinner one is the reference isodose line. This is the 100%. And you can see the very nice coincidence. The 100% isodose line follows very nicely the shape of the target volume. And the green one is the 50%. A few millimeters from the target volume, only 50% is the dose. And from this follows that the other structures, for example, the lung or the heart, receive relatively low dose. Here you can see in two other views, the sagittal and coronal views, the dose distribution, and again, very nice conformality of the dose distribution to the shape of the target volume can be observed. The prostate cancer is very popular site for the brachytherapy. Using ultrasound imaging, needles are inserted into the prostate, and using the ultrasound images similarly to the CT imaging, the contours, the prostate contours are outlined, and the rectum and the urethra as the organs at risk are also outlined. And here you can see the three-dimensional reconstruction of the prostate. The red one, this is the rectum, oops, and the small red dots are the source positions. Here you can see the verification X-ray image. There is a Foley catheter filled with the contrast material in the bladder. And this is the ultrasound probe, and these are the needles, and the tip of the needles are in the bladder wall. Unfortunately, on the X-ray, the prostate is not visible, but the prostate is somewhere here. So that's why for the treatment planning, we use ultrasound imaging. Here again, you can see the very nice dose distribution. The red means the 100% isodose line, which follows very nicely the prostate. And inside, of course, there are high doses because we are closer to the sources, but it's still acceptable. And a few millimeters from the source, from the target volume, the dose is all very small. So that's why the rectum receives relatively small dose. The cervix cancer can be very effectively treated with brachytherapy. Here you can see applicator and MR-CT compatible applicator. This is called Fletcher applicator. There is a center part which can be introduced into uterine tube, and these are the so-called ovoids. And through the ovoid, some needles can be also inserted. So, and with this applicator, if we have a irregular shape of target volume, like here, but with this applicator, using these extra needles, the dose distribution can be again very conformal. The isodose curve, the reference isodose curve, follows nicely the shape of the dose of the target volume. And here you can see again the three-dimensional reconstruction. The red one is the target volume, which we have to irradiate. Here are, you can see the applicator and the needles. And here, this is the bladder and the rectum as the organs at risk. Brachytherapy can be used for head and neck tumors as well. Here you can see a base of tongue tumor. It's a small one, and plastic catheters are inserted into the tumor. And again, using the CT imaging after reconstruction of the catheters, here you can see the catheters in three-dimensionally reconstructed. Here again, you can see the target volume, and here again, the dose distribution. Again, the 100% isodose follows very nicely the target volume, and the blue isodose line is only the 50%. In this case, the mandible, the bone, is organs at risk. We have to protect the bones, and with brachytherapy, this protection can be done very nicely. Compared to the external beam, the dose to the organs at risk generally is lower with brachytherapy. Bronchial tumor can be also treated with brachytherapy. Here you can see a CT-based intraluminal bronchial brachytherapy. 2 catheters are inserted to the bronchi. And here you can see the target volume, the red one, the 2 catheters. And again, after the reconstruction of the catheters and after defining the target volume, we can define the source positions, and we can make a very conformal dose distribution. So here again, you can see locally we can deliver the dose, and the surrounding normal tissues receive relatively low dose. This is the main, most important thing in brachytherapy. Esophageal cancer can be also treated. Here, one applicator was introduced into esophagus, and here again, after the CT imaging, we can define the target volume, we can define where the sources should stop, and after that, we can define the dose at a given depth from the catheters, and then locally, again, we can deliver the dose, and the other structures, again, receive relatively low dose. Here again, you can see very concentrated dose to the target volume. Of course, the brachytherapy is an invasive procedure, but dosimetrically it's very. This is my last slide. Here you can see 2 brachytherapy journals. These journals are dedicated only to brachytherapy. On the left side, the Journal of Contemporary Brachytherapy. This is the European journal, official journal of the Polish and the Indian Brachytherapy Society. And on the right, you can see the Brachytherapy journal. This is the official journal of the American Brachytherapy Society. So brachytherapy is a very important treatment technique in radiation oncology. And in these 2 journals, many clinical studies and physical articles are available for using the brachytherapy. Okay, thank you for your kind attention. And if you have any questions, just ask me. Thank you.
Thank you very much, Tibor, and thank you again for being so flexible. Okay, so we have a bit of time for questions. Are there any questions? I don't see any questions in the chat, but maybe somebody would like to ask a question live now. Okay. There are no questions for the moment. I'm checking whether I see a hand or something like this. No. Then we can maybe, Tibor, can we also give your email, and then people can directly address you if they have a question still coming up. I think you will also, after the break and after Niklas' presentation, you will also do some more practical work maybe than the questions coming up.
Yeah.
Great. Okay. Thank you very much.
Thank you.
Yeah.
Bye-bye.
And now, so we will now have a longer break. We will break until 10:45. This should give you also the occasion to watch the presentation of David. Again, apologies. Okay, so yeah, I will see you all at 10:45, where we start again with the lab of Niklas Wahl on proton therapy. And yeah, me and Mattia, we're going to check something now with regard to sharing, whether we can find a solution. Okay, have a good break and see you at 10:45. Okay, Mattia,
Yes, here I am.
1 second. Can you maybe stop streaming on YouTube for the second?
Yes, but if I stop, then we have to restart with another video. I can stop.
Okay. Then no,
I can
then
stop recording. By the way, just.
Okay, super. Okay, so then let me try and share my. I'm just going to click on the video. It doesn't matter whether I take it from there. Okay.
Hi there. That is study Megan.
So. Okay, let me. Share my screen. Okay.
Kirsten, may I share one video because I have several downloaded video before I upload it in a drive. Maybe we can try to share this video.
Okay, you mean it might be the quality of the video. Let me first try and share the video that you just shared. Okay, here I can see it clearly. The question is whether I put the voice correctly. Can you see me? Oh, I'm frozen now.
Now I can see only that you would like to share your screen.
Okay. So my internet somehow doesn't, it's too much for my internet, I think. Let me.
Now we can see this and it's nice.
Yeah, I think it was an issue with my internet. Can you let me play this? Can you also hear this? 1 second.
It is a very, very
Low voice, but you can hear it?
Now it's better.
Okay, oops, now I closed it, never mind. Okay, can you
Okay, I will also try from my computer. What do you think?
Okay, good. Yeah.
Just stop the screen sharing.
Stop share.
Yes. Now I am going to try another one, and after that, this for David. I try to share this brachytherapy practice, what we Tibor have.
My name is Tibor Major. I'm a medical. My name is Tibor Major.
Just
we can hear it, but we
yes,
cannot.
because I cannot share. Can you see now?
Yeah, we can see it now. Yeah.
Yes,
I'm a medical physicist working at the National Institute of Oncology.
Is it good?
Yes.
Video, I will show you the brachytherapy equipment.
Okay.
It is okay now?
This one is okay, yes.
Okay, then I will share Tibor's video from my computer.
Okay, so you will share from your computer. Good.
Yes.
Yeah.
Just wait a minute. I try to look. I want to look at the video from David. Just a minute.
This
Okay.
means the activity.
And I also have one more. Just first for we will have tomorrow another video from radiation protection. Máté Lajos.
Yeah.
Dear ladies and gentlemen, my name is Máté Lajos. I'm a physicist. And I will
Is it good?
Yeah, this is good.
Such as sources,
And the voice and the screen also.
Yeah.
And so on.
Okay. Then now I try this David video. Just I have to find it because I have only in the drive. Maybe do you share the screen from the drive or you download it in your computer?
Well, just now before I simply shared it from the drive because I simply went.
Yes, but I think that this is the problem because if you download it in your computer, the videos after that, I think it would be nice.
Okay, but I think with me it worked. I don't know, Mattia, did you download the video or
No,
did you?
no. I share from a drive.
I think, Mattia, this is the problem because
yes, probably yes.
Now I try to download David videos from to my computer. Just a minute. Sorry, I need some minutes.
No worries. We have until 10:45.
Okay. Because I was uploading it at home and I'm now in a hospital and I had it only on Drive. Okay, now I have it downloaded. Okay, and then share.
Hi there.
Is it good now?
Yes.
Yeah, then that's the problem because the drive is too slow.
Okay. Yeah,
What
so Sila,
is the
I already.
punchline? What is the message I'm trying to stress now? That is that.
Okay.
I downloaded also the brachytherapy laboratory, so
Okay.
I can share it later.
Okay, good, Mattia. You can try if you have now the time. You can try to share it, and we can see this.
I can try now. Yes, just 1 second. This one. Share sound.
My name is Tibor Major. I'm a medical physicist working at the National Institute of Oncology Budapest and at the Semmelweis University Budapest.
Okay, is it okay?
Yes, but I think it's still a bit blurry.
Which was better, Kirsten?
Yours was better, Sila.
Then I will run it.
Yeah,
Okay, because I'm here and
yeah.
I can run it.
Mattia, I'm afraid it might also be linked to your computer.
Maybe because today also we have problem with the phone, so I don't know. But internet is working. I mean, maybe it's not the faster, but yeah, we don't have signal in our phone, for example. So
yeah.
Okay, then I will run for Tibor, and for tomorrow we will see.
Okay.
Okay.
Good. I think, well, fine. I think it can work like this. So great. So we'll see each other at 10:40. 10:40.
Okay. 50 minutes. Okay.
Okay. See you then. Niklas.
Hey.
I just saw that you arrived. You want to try testing new video?
Yes, I cannot share my screen because someone else is sharing the screen. Probably it's because of the music. Maybe it works. Yeah, now it works. So, does this work?
Yes.
Perfect. Then I stop sharing again for now.
Okay. Good. Okay. Okay, so let's wait some more minutes until 45 until everybody's there. Okay.
Yes.
Sound is also very nice, and your picture is very nice, a bit of holiday.
Yes. Like on the weekend, I did the German thing to do, like hiking up the Zugspitze. Finally, never been there. Always only been to Austria, and now I've been on the highest mountain in Germany.
Was there snow or?
A little bit was left, but you know, it's not that high. It's 2,900 something meters. So I'm half Austrian, so the Austrian part of the family always used to say the Germans are envious of the Austrians 3000s, and the Austrians are envious of the France's with 4000s. So there was a little bit of snow left, but not much. It was super warm, super sunny.
Ah, nice. We have a really, well, a very miserable June here. So all the water that made, well, it's 16 degrees and not very nice. But okay, at least we have the nice picture while you're talking.
Yes. Little bit of holiday feeling then.
Okay, I'll have another coffee and then we meet, well, in a minute already.
Yes.
Okay, here we are already back. Let me see. So yeah, we're still 28. Nobody in the waiting room as far as I can see it. So let's just, yeah, Mattia turned on the recording. Perfect. So I think we're ready to start. Go ahead, maybe present yourself, Niklas, and then we learn all about proton therapy.
Yes, thanks a lot for giving me the opportunity to show a little bit of the practical side of proton therapy. I'm Niklas, like Joao Secco, who gave the lecture on proton therapy this morning. I work at the German Cancer Research Center in a slightly different department though. So it's the Department of Medical Physics in Radiation Oncology. And I'm leading a small subgroup there, which is called radiotherapy optimization. So basically, we deal with everything related to planning treatments. And so I also work often with Joao, and so this is quite a good match that I can show the practical side. Another thing we do, and that's also how I'm going to show you how proton therapy looks in practice. So it's not clinical practice exactly, but close. We develop a open source toolkit for where you can do radiotherapy planning, proton therapy planning, and research, specifically research with it. And you should see on the screen now the interface, the graphical user interface of this open source toolkit. It's called Madrat. If you are interested, you can go here, download it. You can start coding when you have MATLAB or Octave, or you can just download the standalone and play a little bit around with treatment plans yourself. It takes a while to get into, but I will show you now a little bit what's going on. So what we see loaded here is an open source, like an open data patient from an openly accessible data set. So the patient volunteered to get the image taken. If I've seen correctly in the program, you already got the first insights into images. You also got, I think, insights into brachytherapy. So you already know your way around a little when you look at these images. But maybe just, I don't have that much time, so maybe just a little bit of discussing the patient. So what you see is a computed tomography image in Hounsfield units. So you see like these are, they are basically representing the attenuation in a voxel, which is a three-dimensional pixel, measured from rotated, basically like Röntgen pictures taking under rotation. So you see basically in every pixel how well this attenuates photon beams, where -1000 is like air or near vacuum, 0 is exactly water, and then you go upwards towards the bone regions, and you see that most of the tissue stuff is around the 0 region, maybe 100, something like this. And you can quite clearly see that there's some air, so this probably will be lungs. So if you look at this, you can probably see that this is lungs. You see a structure here with a little bit of a bony part, which is the spinal cord, and so on. What you also see is that these structures are segmented. So they have contours, so someone sat there and drew a contour. So for example, here you see the spinal cord, you can see this here. There is some margin around it, and Joao Secco mentioned this earlier, that we have these margins, which are basically there as for safety regions, like for mispositioning. We will come to that later as well a little bit. You see also the heart here, which is quite big, and you see the liver starting here. So we can also maybe quickly check another position. So here you see the table where the patient is lying on, and now you see a little bit clearly this is the liver, like directly below the lung. And you have some other structures here, which represent the bowels and the kidneys and so on. So, but that's we don't want to like look at every individual organ. So we use quite often these extra slides, and there's like some structures here around this X. I will explain what this is. So basically you have here someone found a tumor, and the tumor is designated as GTV, which is the gross tumor volume. So basically you do not really see the tumor here. It's a CT image. There's also another reason why you don't see it, but I don't want to go into detail that. But here could be a tumor. And the tumor, like what you see on the image, it could also be an MR image that you have taken and registered to that image, is called the gross tumor volume. And then the clinician says, wait a minute, we know we don't see everything on the image. So I know from like empirical evidence on tumor studies and so on, that there's some infiltration. And so I draw a slightly wider image. Someone has his microphone on. Could you please mute your microphone? Thanks. So yeah, so basically we have the slightly wider margin, which is not isotropic. So it's quite isotropic in the liver, but you see here is kind of some interface to the lung and to the center here, to the heart. So we know that it cannot infiltrate, it will not infiltrate over here. So that's basically what the clinician says. I know that there's at least some infiltrated tissue that you don't see on the image. And one, this is called the CTV, the clinical tumor volume. And then there's another structure, which is the so-called PTV, which is basically a safety margin, like here around the spinal cord, to make sure that even under shifts of the patient, you still cover the CTV. And this is called the planning target volume. So that's basically names you might have already heard. They came up in like in side sentences or something like this. But that's basically what you need to start to think about the actual treatment planning. So you know where your tumor is, you know where you want to plan on, you know where your critical structures are, which should not get too much dose. So what you also see, not everything is segmented. So the bones here are not segmented. So everything which you know it's quite tolerant and not super critical to irradiate will not be segmented, only the critical structure. So for example, if you damage the spinal cord, that can have quite some big consequences post-treatment, because it's like a cut to the cord, and the patient may be paralyzed. So, and you can directly imagine that especially the spinal cord and the heart might be organs that you should really not damage here, and there's like quite some strict constraining here. Okay, so now when we want to create a proton therapy plan, we need two things. First, we need to compute, we need a dose calculation algorithm. So we need to compute the energy that a proton beam deposits in the patient at every point. So that's not like this, I mean, you're at at the correct summer school for that, so I guess you also have the background, but you do not care about total body dose now, so which you often measure in sievert, but you care about local dose in gray. So that you need to know for a proton beam really locally in every image point / voxel. And the other thing is that you need to find a way to create a dose that matches basically that does not damage these critical organs too much, but irradiates the tumor. So you saw this curves that Joao Seco showed, that you basically want to maximize the tumor control probability while minimizing the normal tissue complication probability. So that's that dose you need to find. So that's the difficulty here. And I think the most important thing I want to show you is why proton therapy is so interesting. I think Joao Seco said it, but I think the first thing I want to do with you is show you like compare protons and photons with each other. And I want to do this a little bit of interactive, like little bit interactive. So with some feedback from your side, I hope I see the chat. Maybe let me open the chat so I can see something. So let us start to try to irradiate this patient with photons. So what you do is basically the photon lies off a table. You define the center of rotation around which the irradiation device rotates. That will be directly in the tumor. Makes most sense. We call this the isocenter. And then you can choose a beam incoming angle. So we stay in this plane now, in this actual plane. And maybe someone just suggests a beam angle from which we want to irradiate. And we choose that. So should probably not be an angle that directly shoots into the heart. So maybe suggest something. At the moment it's set to 0 degrees. About 180 degrees would be maybe an idea. Point here is you shoot through the table, but let's just do it. Let's just try 180. So I also have a little bit of fun, and I have never done a 180-degree plan, I think, here. But you shoot now, we shoot up through the table from below. So we pass the heart, and we do not shoot through the spinal cord here. With 270, we would basically directly stop in front of the organ, which would be nice for protons. But let's start with the 180 now, and do a dose calculation. So now I choose a dose calculation algorithm in the background. So which will pre-calculate a dose, and nothing happens. So why don't I have a dose? So what the computer or the program just did is basically it computed dose normalized to some initial amount of photons I'm going to send into the patient, but I have not decided yet on how much photons I want to choose. So there's nothing shown yet. The second thing I do, and so basically I now know a normalized dose in the background. It's stored somewhere. And the second thing I do is I want to decide how much photons I'm sending from where in my beam, so that the dose looks nice or matches, basically does not irradiate too much healthy tissue. This is done in an optimization step. So the optimization step, I can build an objective function. So mathematically, I build a function that describes my goals that I want to achieve. So for example, in the PTV here, I want to achieve that I want to achieve a dose level of 45 gray over the whole treatment. And there I do basically a squared deviation objective, which is just the least squared. So I optimize the dose to not deviate from 45 degree. And I can also put other objectives there. So at the moment, I only have the skin, which basically describes the whole contour, but I could put the heart there. So the heart is like this, and there I penalize overdosing. So I want to stay below a certain dose. So let's maybe choose 15 here, and like I could choose 100 here, and so on. So this is how I can build a mathematical objective function that I then optimize. So what is exactly is optimized? On the one hand, so you see now some optimization, the objective function decreases, it's get minimal. It's getting like it tries to find a minimum. So what am I exactly optimizing? The first thing that I'm optimizing is dose. So that's how I define my objective function, but my dose depends on the fluence I choose for my photon beam. So the optimizer actually chooses the fluence for the photon beam. And you directly see with photons, it's quite difficult with one photon beam, which has this exponential decay of energy deposition due to Compton effect and photoelectric effect and so on. Here it's mostly Compton effect, that you really cannot cover the tumor nicely. So you have a very high dose at the entrance, so you will basically destroy the skin there, and the low dose behind the tumor, and the tumor does not have a homogeneous dose. So that would be probably unfeasible, and the optimizer cannot find a good setup because you do not have enough degrees of freedom here to shape the dose. So since you will, I think, also get some lectures on photon techniques, I will not go into detail here, but we can try the same with protons. And for protons, you know that we have this Bragg peak. So our energy deposition in the medium is not exponentially decaying, but it is more or less increasing with the power law. So, and then due to range stacking, you get the shape of the Bragg peak. Joao Secco showed this quite nicely before. So if I do the same calculation with a proton beam, I do the same again. So what I'm pre-computing now, so with protons, this is much more intuitive, what I pre-compute in the back, because you remember that Joao Secco showed due to energy variation and the scanning magnets, I basically can send in a lot of small Bragg peaks into the patient and scan a tumor volume. We call this intensity modulated proton therapy because we modulate the incoming fluence / intensity of the individual Bragg peaks to create the spread out Bragg peak. So this is very intuitive with this one beam. So we now basically for a lot of individual Bragg peaks, this can be thousands of individual Bragg peaks with different energy and lateral position, we decide in the optimization step how many protons we want to send in there. The computer already in the background basically laid out where he wants to put the Bragg peaks. So we don't know this yet, but we can now optimize and let the optimizer decide how to how much protons to send in from every Bragg peak. So there will again be an optimization step. So you see, it's just minimizing a function. So when I show like something to school children, I always say that's why you need to pay attention when you discuss functions and curves in school, because you can be like so many problems can be described as a minimization problem. And now you see the proton spread out Bragg peak. So you see just from one angle, the entrance dose is now much smaller here. Let me show something. So it's now much smaller here. The maximum of the dose is within the planning target volume. And you do not have this decay. You have also quite somehow homogeneous dose here. It's not super homogeneous, but I think it's okay. It's not that homogeneous because we go through lung here. So that's why I really do not like the 180-degree angle too much. But we will see this, we will discuss this on the next patient. So again, just to tell you what happened here. So I, as a planner, I chose an angle, which I thought was good. So 180 degrees. I might probably more consider the 0 angle or something from here, or something even from slightly less, so that I pass a little bit less lung. And then I set up a planning scenario, so where I basically put in my organs and tell the optimizer, here is a part of the objective function that I want to build, and minimize, that describes that I want to not overdose my heart too much, and I want to achieve a homogeneous dose, and so on. So this is this is not a clinical system. So clinical systems give you a lot more possibilities here. So that's kind of the classical way of optimizing or planning. In new systems, you would also have stuff like multi-criteria optimization, where you basically get a whole set of plans and then can weight them. Here you do it by applying penalty factors. So if you decide the heart becomes more important, you set this, for example, to 200, so make it double important, and optimize it again. So basically you can modify your objective function here in a trial and error fashion. So that's what earlier has been done for a long time in radiotherapy treatment planning, and now the techniques are getting more and more sophisticated. But that's the basic thing. Always what you have to do as a planner in proton therapy is you decide how you want to play the prescriptions that you get. And you always have to work with this trade-off of covering the tumor and trying to minimize the damage to the organs at risk. So if I'm basically, I know I can cure the patient. So with just radiotherapy, I would make it very important, or like it's the primary goal then, to really cover the tumor, and the patient would probably be okay with having maybe a little bit stronger side effects than in a palliative treatment, where you basically know you cannot cure the patient, but you can basically destroy the tumor, maybe the primary tumor, not the metastasis, but the primary tumor. But you also do not want a patient that you treat palliatively to suffer from severe side effects, because it's not the sense of a palliative treatment is life quality. Okay, so that's basically how you build as a planner your objective, your problem of how to create the dose, or how to shape the dose to your respective targets. So that's basically, like, we do not have so much time. I can show you much more, but that's, I think, the essence you should take out of it. So now to some proton therapy specifics. So this works, as you've seen, it works for photon therapy, not with one beam, but you will I think there will be something about the cyberknife and so on. So you will hear a lot of different ways on how to deal with photons. So photons are really, just also to remind you, the standard modality of treatment. Proton is the exotic way of treatment. So one thing I want to show you is that what is actually, if you look here at this color scale, so I see a dose. The dose is not what I have given here. That's because the patient doesn't come in one session, it comes in multiple sessions, and this is already basically calculated for the patient to come in 30 fractions. But if you look at this label here, it says RBE times dose. So it was also quickly said in the proton session, protons have a different radiobiological effectiveness of compared to photons. Does someone remember what Joao Secco said it was? Maybe. What did he state as radiobiological effectiveness of protons compared to photons?
About 1.1.
Yes. So he said basically, yeah, like just take a radiobiological effectiveness of 1.1. This is clinically really done, but please remember that this is not the case. So what you see here is actually the physical dose in gray multiplied by 1.1. So if I go to the physical dose here, I will start to see like a slightly less dose. So if I switch, it's exactly the factor 1.1 that is applied. So this is clinically acceptable, but it's not exactly the case. Okay. Remember that there is like some variation because the radiobiological effectiveness actually depends on how the energy is transferred locally. So you can think about the DNA. If there's some cannonball rampaging through it, it might create directly a strand break, a double strand break. So if the dose is deposited very locally within the DNA, this is much more effective than if the dose is basically homogeneously deposited, not as locally like with photons. But protons differ not so much, but depending on the energy they lose, this radiobiological effectiveness changes. This is much more evident for carbon ions. So I will really quickly just show you how this looks in a setting where this variation needs to be really accounted for. So this is not proton therapy anymore, but carbon ions. But I really quickly want to show you this. So nothing happens. I have calculated my carbon dose. I will optimize my carbon dose. This will take longer. So a little bit. You already see that there's something different going on because it takes so much longer than the previous settings. So let's see, it should stop soon because we only have one beam. It is quite small, but can also stop it early if it takes long. We still have 5 minutes left, so I will just, I think I have enough time. Okay, I think I will stop it at 100. Oh, it actually exactly solved to 100. So the first thing you will now see from the dose is that the entrance dose has apparently reduced, and there is like a tail behind, which is a very slight tail of fragmented ions that have higher range than the carbons. So the carbons, when they have nuclear interactions, they might fragment. So you get some lighter ions out of it, and that produces this tail. But what I wanted to show you, I'm again showing RBE weighted dose. So the optimizer, my planning system directly correctly planned on the RBE weighted dose. But for carbons, it's absolutely unfeasible to plan with a constant factor. So if you look at this somehow homogeneous RBE weighted dose in the tumor here, and you compare this with the physical dose, you see something like this. So it's completely unhomogeneous. You have like a hotspot here, and then the dose decays. And this is because the RBE of the carbons is definitely not constant with depth. So in principle, you have the RBE increases with depth. And so that's why you have basically this hotspot here. And then the physical dose needs to decrease. So your RBE weighted dose is homogeneous. It's the same principle also for protons, but this variation is so small that you often assume 1.1, but keep in mind that this is not an exact factor. So in the last 3 minutes, I want to show you another, let's say, problem of proton therapy, and I will switch the patient for that, which this is basically now a head phantom. Okay, so there is kind of an artificial, so it's not a real head, it's really some head that was pieced together from materials and built. It's very useful for quality assurance in treatment planning, so that you can pre-calculate plans, you can insert ionization chambers and so on. So you would really put this then on the table and do some plan for it and irradiate it and measure if the machine is doing what it should be doing. So you see this head phantom here. It has the temporal lobes. It has a brainstem here. It has a target here. It has like artificial eyes and optic nerves. So all the important structures are there. And I'm now going to create a proton plan with 2 beams. So this is really very fast on this phantom because it has a very bad resolution. But that it is so fast is nice for demonstration purposes. So I'm again doing the same steps. So you see it's really fast. I could already calculate those, optimize those. So we'll be done soon. And I think I should be then exactly on time. So this is a second thing, which is basically this now highlights a problem in proton therapy. So what you see here in this phantom, so I can maybe quickly remove the dose, is that it is very heterogeneous. Okay, so we have like really the nasal cavities have quite a lot of air. We have these channels here that have quite a lot of air. We have like bony structures that make a very strong gradient between the density and the stopping power of protons. And the problem is when something is this heterogeneous, the dose is no longer homogeneous because you kind of degrade the Bragg peaks. So the Bragg peaks, some part of the proton beam goes to denser tissue, some part of less dense tissue, and then you get these Bragg peaks. And you see we have this PTV margin here again, which is a safety margin for displacements. But the problem of these heterogeneities is also that if I shift the patient, which I'm going to do now, I will shift the patient by 2 millimeters in Z and Y direction, recalculate my plan. These safety margins are not enough for proton therapy. So because when I shift the patient, I may end up with a completely unhomogeneous demodulated dose in the target. And my margin that I took is no longer valuable. And this is why Joao Secco also earlier highlighted we need in-room imaging and so on. So proton therapy gives you a lot of precision due to the Bragg peak, but precision also comes with uncertainty as soon as you change something. The anatomy changes, the patient shifts, so you need to be extra careful there. Okay, so this was a half an hour lab on proton therapy. So was quite quick. But I hope you get a little bit of insight. What are the problems, the biological side, the uncertainty side, and what are how nice these Bragg peaks look, and how easy it is already with 1 or 2 beams to create a nice dose on the other side. So thanks a lot for listening.
Well, thank you very much, Niklas. Thank you for this interesting presentation and interactive presentation. Very nice tool, makes you feel like playing around with it. Are there any questions? I cannot see anything in the chat. Well, maybe, well, okay, so maybe Niklas, if you just would put your email address in the chat, maybe people would like to address you. Well, it's already there. Okay, perfect. Yes. So they can ask you privately in an email for more questions. Okay. So thank you very much again, and yeah.
Thanks
for this nice presentation. Okay, so we move to the next one, which will be a lab from Tibor Mayer again, and Sila is going to launch the video.
Okay, can you see it?
Yes, we can see it.
Good. And just.
Okay, so Tibor will be available for questions.
Yes, Tibor is here. Yes, he's here.
So if you have questions, just put them in the chat, or yeah, Tibor can answer them.
My name is Tibor Mayer. I'm a medical physicist working at the National Institute of Oncology, Budapest, and at the Semmelweis University, Budapest. In this video, I will show you the brachytherapy equipment. We are here in the brachytherapy treatment room, and this is the equipment which
Sila, did you do something? The tone is gone. I mean, it's good that the text is there, but I cannot hear anything anymore.
Is it okay now?
High doses.
Yeah, I think you should stay
Afterloading
unmuted.
means that during insertion of the applicator, the radioactive source is not present. It is an inactive procedure, and the source will be only loaded into the applicator with remote control technique from outside afterwards. Currently, the radioactive source is in the head of the machine. Here, in the center, there is a container with a thick wall and made of high-density material. And this is how the source looks like. The iridium-192 isotope is in a capsule, which is fixed to a metal wire. The wire is wound up to a cylinder, and its end with the source is in the center of the container. When we start the treatment from outside, a stepping motor drives out the source through a transfer tube into the applicator. We have to specify where the source should go and how long it should stay. This is calculated by a software, taking it into account the prescribed dose and the tissue depths where we want to deliver the dose. But generally, we don't want to irradiate only in one position. And in that case, the wire pulls back the source in a few millimeters into the new position and irradiates for a predefined seconds, and so on. This is called the stepping source technique. Having only one source, but by moving it step by step, we can irradiate any lengths. When the treatment is finished, the source is driven back to the container in the machine. You can see an applicator with only one channel, but there are applicators with 2 or 3 channels. And in interstitial brachytherapy, lots of catheters or needles can be used. There are 30 channels available in the machine. In case of multiple channels, the channels are connected to the machine one by one. These are the transfer tubes which connect the applicators to the machine. Depending on the type of applicator or catheters needed, different tube has to be used. We make sure that the source will go to the appropriate applicator. So the source first goes out from the channel 1, then performs the steps in the applicator and goes back to the machine. In case of multiple channels, the source goes out from channel 2, performs the irradiation, and so on. This procedure continues as many times as channels we have. With this technique, having only one source, we can substitute lots of source distributed in the target volume. And the final dose distribution will be formed by dose contribution from one source, sent in different well positions with different well times. This afterloading technique is very safe regarding the radiation protection of the staff because practically they don't receive any extra dose during the treatment. This is the main reason why this technique, the most widely used brachytherapy treatment method, is in the world. Some physical data about iridium-192 isotope. It has gamma irradiation with average energy of 380 kiloelectron volt. As you know, gamma radiation, electromagnetic radiation, and the half-time of the iridium-192 is 74 days. During this time period, the original activity will be half, and the treatment time will be double. As the activity decreases, the treatment time will increase continuously. In 74 days, the same treatment will take double times. In order not to have too long treatment time, the source is regularly replaced with a new one every 3 months. As the activity decreases, the irradiation time increases. The initial activity of the source is 10 curie, which is regarded as a high activity. That is why the machine is called high dose rate after loading. HDR means high dose rate. From this follows that one irradiation takes 5, maximum 20 minutes. Due to the short treatment time, more patients can be irradiated daily. And during a 3-month time period, lots of patients can be treated with the same source. In 3 months, we replace the source with a new one. A few words about treatment planning. Similarly to external beam radiotherapy, nowadays CT-based planning is used in brachytherapy also. CT imaging is performed after the insertion of the applicators or catheters, which are then reconstructed on the CT images. Target volumes and organs at risk are contoured, and with a special software, the source dwell positions and dwell times are calculated depending on the prescribed dose. Here in the treatment room, you can see a C-arm X-ray machine, which is used for verification purpose only. After insertion of the applicator, an image is taken and its position is verified. Here I show you a verification image with an applicator used for gynecological treatment. The metal intrauterine applicator is nicely visible, and it contains a marker with small dots with 1 centimeter separation, simulating the source positions. It also provides a scale which helps us calculate the irradiation lengths. The position of the applicator can be related to anatomical regions, especially to the bony structures. As I mentioned before, the treatment planning is based on cross-sectional imaging, mainly using CT images. But for example, the prostate implants are done under ultrasound guidance. And during the planning, transversal ultrasound images are used. With this monitor, we can supervise the patient during the treatment. With the treatment, only the patient is inside the room, the staff is outside and watches the patient on the monitor. In case of any problem, the staff enters the room. And in such a case, the source automatically goes back to the machine in a protected container to prevent the irradiation of the personnel. When a new source is loaded into the afterloading unit, it has to be calibrated. These are the tools which are used for the source calibration. On the left side, the well-type chamber with the applicator with the source, and there is a special insert. On the right side, there is an electrometer for measuring the charge. This is the schematic view of the well-type chamber. You can see in the center of the insert, there is a source, and the applicator is connected to the afterloading unit. And here you can see how we can calculate the activity or the reference air thermal rate. There is an equation with 3 parameters. The first one is the calibration factor. The second one is the measured ionization current. And the third one is the air pressure and temperature correction. Because inside the well-type chamber, the air density can be different according to the pressure and temperature. That's why we have to calculate at the time of measurement this correction factor. The reference activity or air thermal rate is read from the certificate for the sealed sources on the left side. And using the special Excel sheet, we can enter the measured charges. We can enter the reference air thermal rate, and we have to enter the date of the measurement. And from these data, we can calculate the current source activity. Here you can see the ratio of the measured and the manufacturer's certificate activity is 0.982, which means the deviation is less than 1.2%. Anyway, the acceptance criteria is plus minus 3%. The measuring cable outside the treatment room is connected to an electrometer. Inside the treatment room, the other end of the cable is connected to the well chamber. The chamber is positioned on a small stand in order to minimize the scattering from the floor. This is the afterloader unit. And there is a special insert which accommodates the source. During the measurement, the source will be positioned in the center of the insert. Here I put the insert into the chamber and connect it to the transfer tube. The other end of the transfer tube is inserted in one of the channels of the afterloading machine. With a special key of the afterloader, it is switched to a position of ready for irradiation. This is the setup with the ionization chamber and the afterloader. The door of the treatment room has to be closed before starting the irradiation. This is the electrometer again. From the afterloader's control computer, a special radiation program has to be loaded for the source calibration. The actual source parameters can be seen on the screen. And then we accept the loaded data. on the control unit, we can initiate the radiation. The color lights beside the door show if the source is in the treatment position and there is radiation in the room. Now the source is in the center of the well-type chamber and the measurement is being carried out. On the electrometer, we can see the measured charge in microcurie. One measurement takes 60 seconds, and now the measured charge was 2.168 microcurie. To check the consistency, we repeat the measurement at least 3 times and calculate the mean of the readings. Using the simple Excel sheet, we calculate the source activity. And here, the ratio of the measured and manufacturer-stated activity is 0.982, meaning 1.2% deviation. And after the measurements, we remove the transfer tube. In the next step, in the next exercise, we check the accuracy of the source positioning. There is a special tool with a glass window and a millimeter scale. The transfer tube is connected to this tool. The source is driven out to a position of 200 millimeter. And here we can see that the source at the end of the cable is stopped exactly at the 200 millimeter mark, meaning an accurate positioning. In case of deviation, the positioning can be corrected with the software. And here again, the very accurate source position can be observed.
I hope that it is the last slide. Tibor, is the end? Okay, can you hear me?
Yes, I see. Yes.
Okay, good. Then it is the end of the video, and now he's Tibor who can answer to your questions. Do you have any question?
Okay. I think it was a very nice and clear presentation. I really liked the fact it was even with subtitles, so everybody could see it as well. Well, I think if there are no questions like this, well, we simply start with a break. And then we resume at 12 o'clock for the quiz.
Okay.
Yeah? Okay. So everybody can get ready for the quiz at 12 o'clock. Yeah? Okay. Good. See you then at 12 o'clock. I'll put this in the chat that at 12 o'clock, maybe be here at just before, so we can also share the link and prepare everything. Okay. See you then. Bye.
Bye now.
Okay, I see we have 29 participants. Well, minus Sila, Mattia, and myself. Thibaut, not Thibaut. So, and I see that Mattia already posted some information into the chat. We'll still have some time. Wait until everybody is ready. But you can already click on the link in the chat and register. Okay, I see a question from Luca in the chat, and I'll answer over the microphone because I think it's. I heard this question before, so it might be of interest for everybody. So there are several people who will follow both sessions, medical physics and nuclear energy, and you can participate in both quiz. There will be, and you can win both prizes, obviously. So it's your choice. Either you only listen to one and participate in one of the quizzes, or you participate in both.
Yes, so we will have a separate ranking for the medical physics and the nuclear energy. So for yesterday was just a general quiz, so points will go to all participants. Then today we will have a separate quiz for you in a medical physics session, and then later in the afternoon for the nuclear energy. But we will calculate the final sum in a separate way. So you can join both and see if you're lucky to win both also.
Okay, super. I hand over to Mattia for the quiz, and also Mattia will moderate everything this afternoon. Okay, have a good quiz. Good luck to everybody.
Okay, so let me see. There are already 22 people that registered. If I'm right, we should have around 47, except for me, Xilla, Professor Mayer. So we should have 27 participants. 5 people is still missing. Okay, 4 people now. I can send once again the link for the one who logged in a bit later. Just 1 second. Okay, this is the link to join and register to the quiz. Please, again, rename your avatar with your name and surname, because if not, it will be very difficult to find who answered and to calculate the correct points. Yesterday, I have to remark 2 participants that with no name. So if you had as avatar a volcano or a flag, please write me in the chat and I'll add your name to the ranking. If not, I don't know how to calculate the points for that participant. If you remind to have had a volcano or a flag as an icon yesterday for your avatar, please write me here in the chat. So let me see. Okay, we have 25 participants. I start sharing my screen, waiting a bit more. 1 more minute. Just 1 second. Okay, 26, maybe only 1 is missing. Once again, I suggest you to follow not the Zoom video, but the link you are using, because the video quality would be definitely better than mine.
I think, Mattia, with 26 you're complete, because I count 30 participants and we are 4 which shouldn't participate.
Okay, perfect. So we can start right now. I remember you. 15 questions, 25 seconds to answer each question. Let's start with the first one. So for proton therapy, we use protons in the energy range of kilo electron volts, mega electron volts, giga electron volts, or tera electron volts. Only one answer is missing. Okay, everyone has voted, and the correct answer is mega electron volts. Let's move to the second one. The second one is to irradiate a tumor, intensity modulated proton therapy. Use a passive scattering system and compensators, requires the insertion of radioactive materials into the patient, use deflection magnets and varying energy to scan tumor volume. It is a futuristic concept and does not exist yet. 10 seconds left. Yes, once again, everyone has voted. And the correct answer is the third one. Use deflection magnets and varying energy to scan tumor volume. Congratulations. Let's move to the third question. The countdown starting now. So to use a generic margin concept in proton therapy is always safe, only needed in heterogeneous anatomies because of range uncertainties, critical in heterogeneous anatomies because of range uncertainties, or not useful at all. Few seconds left. Okay, everyone has voted, and the correct answer is exactly the third one, critical in heterogeneous anatomies because of range uncertainties. So let's move to the fourth question. Inverse proton treatment planning describes doing normal proton treatment planning backwards, reconstruction of a dose from measurements, processing of a proton tomography image, or optimization of fluorescent dose to fulfill clinical prescriptions. And time is up. And yes, the correct answer is the last one. Congratulations, majority of you. Optimization of fluence and dose to fulfill clinical prescriptions. Let's see the question number 5. The radiobiological effectiveness in proton therapy is considered to be always lower than protons, exactly the same as photons, is known to be exactly 1.1 or is 1.1, but is actually variable and difficult to model. Time is up. Two answers missing, and the correct one is the last one, is RB 1.1, but it's actually variable and difficult to model. Now the 6th question. During brachytherapy, patients are treated from outside with a linear accelerator. X-ray is used for irradiation. Radioactive substance is injected into patients. Sealed radioactive sources are placed into or close to the tumor. Okay, everyone has voted. And the correct is the first one. Patients are treated from outside with a linear accelerator. No right questions. No right answer, sorry. And let's see the number 7. The number 7. Start the countdown.
One
right
second,
now.
Mattia. One second. Can you stop it for a moment?
Yes.
Okay,
Yes,
because I see that Corina has a problem that she cannot see the questions. is this the same with, can everybody else see the questions? Just to check whether there's a general.
I hadn't seen just one question, and it came that I haven't answered at the time. So I just did the question, but not the answers.
Okay, so it was a one-time problem, and it seems.
Yes, yes. I mean,
okay.
I'm sorry for that one, but what can I do?
No worries. Okay, just wanted to double check whether there's not a general problem. Okay, so we can continue.
Okay.
Okay, so let's move to the question number 7, half of the quiz. Now the question is, the natural radioactivity was discovered by Marie Curie, Pierre Curie, Henri Becquerel, or Wilhelm Röntgen? I see all quick answers. And yes, everyone has already voted. And the correct is Henri Becquerel. Let's move to the question number 8. Question number 8. Which radioactive isotopes is used most commonly in brachytherapy? As we saw, among these.
Ne sem dokler me vratil.
Please unmute yourself. I don't know, is the participant mute? Maybe it's Luca. I'm going to mute you. Sorry. Okay. So everyone has voted. And yes, the correct answer is the second one. Let's move to the final part of this today's quiz on medical physics. Question number 9. Which is the main factor determining the dose distribution around the brachytherapy source? Absorption in the medium, scattering in the medium, energy of the radiation, or inverse square law? Five seconds left. Time is up. And yeah, is the inverse square law, as we saw with Professor Mayer. Then let's move to the question number 10. Which tool is used for a brachytherapy source calibration? Well-type ionization chamber, X-ray film, Geiger-Müller counter, or gamma camera? Only 2 answers missing. Everyone is voted, and the correct answer is a well-type ionization chamber. Congratulations. Let's move to the question number 11. Which of the following is enough for producing an image? Facebook application, the camera icon, internet, light contrast, a small hole, a digital sensor, light contrast, digital sensor on paper, light lens contrast, a focus point. The correct answer is the second one, a light contrast, a small hole, and a digital sensor. Congratulations. Question number 12. Which of the following Nobel Prizes were awarded first for medical imaging? For discovery of spin magnetism, discovery of tracer principle of nuclear medicine, discovery of positrons, or discovery of X-ray radiation? Which was the first awarded for medical imaging? So time is up. So the first Nobel Prize went for discovery of X-ray radiation. Congratulations. move to the next question. How many photons are needed for a single positron emission tomography pixel count? Known it's working with positrons, not photons. 1, each positron emission is followed by a photon emission. 2, each positron creates 2 photons flying in opposite directions. 3, each positron creates a coincidence photon triplet. 2 seconds left. One answer missing, and the correct answer is the third. 2, each positron creates 2 photons flying in opposite directions. Question number 14. How is the physics of visible light differs from gamma and X-ray photon physics? Visible light scatters at surface, gamma photons scatter inside the material. They are not similar at all. Visible light interacts with nuclei, gamma photons interact with electrons, and visible light is the same as gamma photons. The correct is the first one. Visible light scatters at surface, and gamma photons scatter inside the material. Now let's move to the last question. Number 15. Why do skeletons appear on X-ray images? X-ray is imaging the soul. X-ray only scatters in bone. X-ray flows around the organs. X-ray is absorbed more by bone. Ten seconds left for this last question. Everyone has voted, and yes, the correct answer is the last one. Congratulations, X-ray is absorbed more by bone. Yeah.
Just one comment for the question 6. There was during the brachytherapy, the right answer is D. It is wrong in the program because it's not A. Not the patient are treated from outside with linear accelerators. The D is the correct. Cells, radioactive sources are placed into or close to the tumor. We can do the 2 things. If you can change the correct answer. If no, drop out this.
Yes, I saw it. Okay, I had.
Okay, it is just some mistakes.
Yeah, maybe in the paper. Yeah, I received. Okay, no problem. I see if I can change it. If not, I can just cancel and not consider that question.
Thanks.
No worries. So for now, let's see the final leaderboard for now. So for today, for the medical physics, very close today too. Daniel Serbak has been the fastest, and the first for today, followed by Tobias Lightgab and Božidar Obradovic. Congratulations to all participants. Then now we are going to calculate with today's results, yesterday's results, and tomorrow's results, the final ranking, and we will see who will be the winner and the podium of the medical physics quiz. Thank you all for your participation.
Well, Mattia, 1 second. So, but this is only preliminary for the moment, no?
Yes,
Until
yes,
you
only for
calculated the question number 6.
Exactly, it's only for today's question, and we have to see if we can consider in a second moment that question, the question number 6, or I'm going to delete it.
Okay.
So if I'm going to delete it, this is the final because no one got point at that question.
Okay.
Okay.
So great. So this led us to the end of this morning's questions. So we are waiting for Mattia's summary of the quiz. And yeah, so now we go into a break because Sila cancels the teams because so we have enough work to do, I understand?
Yes, we finished for today for the medical physics. See you tomorrow at 9 o'clock.
Okay, so we have at least a lunch break for those who will join us in the afternoon, and for the rest, see you tomorrow then. And yeah, after lunch break, it's Mattia who's going to take over the moderation, everything. Okay, see you.
See you.
Bye.
Bye.
Thank you.
Thank you.